Welcome to the podcast. Today, we're diving deep into a fundamental and persistent challenge in statistical physics and computational chemistry, the efficient sampling of molecular systems at thermodynamic equilibrium. This isn't just an abstract theoretical problem. It has profound implications for understanding everything from protein folding to the formation of crystal structures, essentially dictating how macroscopic phenomena emerge from microscopic interactions. The core of it lies in accurately and efficiently drawing statistically independent samples from what's known as the Boltzmann distribution. This distribution defines the probability of a system being in a particular microscopic state based on its potential energy. Simply put, lower energy states are more probable. But here's the kicker. These equilibrium states, these distinct modes of the distribution, are often incredibly sparse and separated by massive, high-energy barriers. Imagine trying to map out a vast, rugged mountain range where the interesting valleys are far apart, and reaching them often means scaling impassable peaks.
So, if these desirable states are like tiny islands scattered across a vast, mountainous ocean, what have been the conventional methods for charting this landscape? And what's the specific bottleneck that makes it such a computational nightmare, preventing us from efficiently finding these islands?
Historically, the dominant approach for exploring this conformational landscape has been molecular dynamics, or MD simulations. MD attempts to simulate the equations of motion of all atoms in a system over time, with finely discretized time steps. Think of it as a brute force tracing of every atomic vibration and movement. However, this approach runs headfirst into a severe timescale issue. MD simulations typically operate with time steps on the order of femtoseconds. That's 10 to the power of negative 15 seconds. But for the system to actually traverse those high-energy barriers, to mix across different metastable states, and truly explore the global energy landscape, we're talking about timescales ranging from microseconds to even seconds. That's 10 to the power of negative 6 to 10 to the power of 0 seconds. This is a staggering 9 to 15 orders of magnitude difference. Consequently, the vast majority of MD computation isn't spent exploring the interesting global configurations. It's spent simulating high-frequency vibrations within local energy minima, essentially rattling around in a single valley, unable to jump to another. This renders MD computationally prohibitive for many practical problems, despite various accelerated MD schemes, which still grapple with this fundamental mixing problem.
It sounds like MD is incredibly inefficient for capturing the full conformational space of a molecule. It's trapped in local minima, spending precious computational resources on irrelevant, high-frequency fluctuations. Given this limitation, Boltzmann generators, or BGs, were introduced as a promising alternative. How do BGs fundamentally differ from MD in their approach to equilibrium sampling?
That's exactly right. BGs offer a completely different paradigm to circumvent MD's timescale issue. Instead of simulating the time evolution, BGs learn a generative model, p theta x, specifically designed to directly propose samples that approximate the target Boltzmann distribution, target x. The genius here is that they combine this generative model with exact likelihoods, p theta x, and the target energy, E x, enabling an important sampling correction. This allows for the parallel generation of independent and consistent samples without needing to explicitly traverse between those high-energy modes. You're not simulating the tedious journey. You're directly generating the relevant destinations. This makes BGs an attractive framework for equilibrium sampling, particularly for larger molecular systems. However, to maintain tractable likelihoods, which are absolutely crucial for the self-normalized importance sampling step, the field has predominantly relied on a class of generative models called normalizing flows, or NFs.
So, BGs sound like a significant conceptual leap, offering a way to bypass the slow dynamics of MD by directly sampling from the equilibrium distribution. But you mentioned a reliance on normalizing flows. Are NFs introducing new limitations, even as they solve some of MD's problems? What are the specific theoretical and practical hurdles with NFs in this context of complex molecular systems?
They absolutely do, and these limitations are quite fundamental to the architecture of NFs. Normalizing flows essentially transform a simple, easily sampleable distribution, typically a single connected Gaussian, into a more complex target distribution through a series of invertible mappings. The core problem is that in their practical instantiations, NFs are not only diffeomorphisms, meaning they are smooth and invertible functions, but also homeomorphisms. This means they fundamentally preserve the topology of their domain. Think about that for a moment. A single connected Gaussian prior can only be mapped to a single connected target distribution. However, the equilibrium distribution of molecular conformations, as we discussed, often consists of several distinct, metastable states separated by high-energy barriers. These are effectively disjoint regions in configuration space, or, if you like, a multimodal distribution with holes or differing numbers of connected components. A standard NF struggles immensely here because it's forced to perform extreme deformations, stretching space across thin, energetically unfavorable bridges, and then compressing it into the separate modes. This leads to highly non-smooth mappings, prone to exploding Lipschitz constants and ill-conditioned Jacobians, which severely limits their expressivity and makes discrete time NFs notoriously unstable and prone to poor sample quality in practice.
So, if I understand correctly, the very mathematical foundation of discrete time NFs, their topological preservation, makes them ill-suited for the inherent multimodality and disjoint nature of molecular conformational landscapes. It's like trying to stretch a single rubber sheet into multiple, separate blobs without tearing it, leading to instability. What about continuous normalizing flows, or CNFs? Do they offer a way around these architectural constraints, or do they introduce a different set of problems?
That's a perfect analogy for discrete time NFs. They simply can't handle those tiers. CNFs, on the other hand, do offer more architectural freedom because they're defined by an ordinary differential equation, specifically a neural ODE. They are theoretically free from the same strict invertibility constraints that discrete time NFs impose. And modern training strategies, such as flow matching, can indeed greatly stabilize their optimization. However, the ill-conditioning problem doesn't disappear. It simply shifts and manifests itself acutely during inference. The learned vector field, which dictates how the distribution evolves over time, often becomes highly non-smooth. This results in what's known as stiff dynamics, meaning you need a very large number of function evaluations from expensive ODE integrators to obtain accurate likelihoods. Remember, these likelihoods are absolutely critical for important sampling in BGs. To compute the log density in a CNF, you need to track the evolution of the divergence of the learned velocity field. This divergence operator requires O(d) function evaluations per integration step, where d is the dimension of the system, which is n times 3 for n atoms. While faster unbiased estimators of the divergence, like the Hutchinson trace estimator, exist, they introduce variance, making them unsuitable for the exact likelihoods BGs demand. So, it's a fundamental trade-off. Discrete time NFs yield efficient likelihoods, but struggle with poor sample quality and limited expressivity, while CNFs are more expressive but become computationally prohibitive for inference due to the sheer cost of accurate likelihood evaluation.
This paints a clear picture of the limitations. Both discrete and continuous NFs present fundamental challenges that hinder effective equilibrium sampling for molecular systems. One sacrifices accuracy and stability, the other sacrifices computational feasibility. It sounds like a new architectural paradigm is needed that can offer both expressivity and efficient likelihood computations simultaneously. Is this where autoregressive Boltzmann generators, or ARBG, come into play as a fundamentally different approach?
Precisely. This is where autoregressive Boltzmann generators, ARBG, enter the scene as a novel alternative. ARBG departs entirely from the flow-based BG paradigm to circumvent these long-standing limitations. Instead of invertible transformations, or ODEs, ARBG employs an autoregressive paradigm to factorize the joint molecular density into a sequence of conditional densities, p theta x equals pi jp, xjx less than j. You're essentially modeling the probability of each dimension of a molecular conformation given all the preceding dimensions, for j from 1 to d. This formulation offers three distinct, and critically important, advantages. First, ARBG overcomes the expressivity bottlenecks of discrete time flows without incurring the prohibitive computational expense of continuous time flows. Second, it inherently avoids the numerical instability associated with learning high-distortion diffeomorphisms, allowing it to naturally model discontinuous jumps and separate modes, the very problem NFs struggle with. And third, and perhaps most excitingly for machine learning, ARBG benefits directly from the immense investment and advances we've seen in discrete generative modeling, particularly those that power modern large language models, or LLMs. It exhibits similar scaling properties in both model size and the number of inference samples, as evidenced by its performance curves.
The idea of leveraging LLM architectures for molecular systems is intriguing, especially considering the continuous nature of molecular coordinates compared to the discrete tokens in language. You mentioned ARBG being diffeomorphism-free and able to handle discontinuous jumps. How does this autoregressive factorization achieve that, and how does it directly translate into solving the topological constraints that plagued NFs? Is it about building the molecule piece by piece in a way that doesn't force a continuous, invertible mapping?
That's a very insightful way to put it. Yes, it's precisely about building the molecule piece by piece, or rather, dimension by dimension, without imposing global topological constraints. Since each p, xjx less than j, is a conditional distribution, it doesn't need to be part of a larger invertible map. This freedom allows ARBG to effectively model the multimodal nature of molecular distributions directly. It doesn't have to stretch or compress space unnaturally to connect disconnected regions. It can simply assign a low probability to the high-energy barriers and high probability to the metastable states without forcing a continuous path between them. This is the core reason it's diffeomorphism-free and can handle those discontinuous jumps in probability density across conformational space. For the first time, we have a scalable, autoregressive, and diffeomorphism-free method for Boltzmann generation that operates directly on atoms in their native Cartesian coordinates. This sequential factorization also has immense implications for computational efficiency. The equation log p theta, x, equals sigma j log p theta, xjx less than j, allows for exact likelihood computation in a single, forward pass. You completely bypass the need for complex Jacobian determinants that discrete time NFs require, and crucially, you avoid the computationally expensive numerical solvers for neural ODEs that burden CNFs. This means fast, unbiased, and exact likelihoods, which is a non-negotiable requirement for effective importance sampling in BGs.
So, by breaking down the problem into sequential conditional probabilities, ARBG gains both topological flexibility and computational efficiency. This sounds like a significant architectural breakthrough for molecular modeling. Given that molecular coordinates are continuous, how does ARBG handle this continuous nature within an autoregressive framework, which is often associated with discrete tokens in LLMs? And what does this discrete binning innovation specifically entail?
That's a critical point, and it's addressed by one of ARBG's core innovations, discrete binning. While LLMs typically operate on discrete tokens, ARBG adapts this principle to continuous molecular coordinates. Instead of predicting an exact continuous value for each dimension, ARBG discretizes the continuous space into a finite number of bins, then predicts the probability of a coordinate falling into each bin. Think of it like a very finely tuned histogram, but where the model learns the optimal binning and the probabilities for each bin. This seemingly simple choice offers profound benefits. It not only provides superior training stability and scalability compared to trying to model continuous mixture distributions directly within an autoregressive framework, but it also unlocks powerful sequential inference time interventions that are simply not possible in flow-based architectures. This discrete binning effectively bridges the gap between the power of discrete autoregressive models and the continuous nature of molecular data, making the approach robust and scalable even for complex molecular systems.
The concept of sequential inference time interventions is intriguing, especially for a system like molecular conformations where small changes can have large consequences. Can you elaborate on what kind of interventions this discrete binning enables? For example, in drug discovery, one might want to explore how a molecule responds to a perturbation or how certain substructures influence overall conformation. Does this allow for targeted exploration or modification within the sampling process itself?
Absolutely. That's precisely where the power of sequential inference time interventions shines. Because ARBG constructs the molecular conformation one dimension at a time, conditioned on all previously generated dimensions, you gain an unprecedented level of granular control during the generation process. For instance, you could fix specific atoms or bonds to certain regions of space, effectively imposing structural constraints. You could guide the generation towards conformations that satisfy particular energetic criteria or specific geometric conditions, such as desired distances between two residues in a protein or target dihedral angles. If you're exploring drug-target binding, you might want to bias the sampling towards conformations that fit within a known binding pocket. Or, in materials science, you could explore configurations that exhibit desired structural properties for a novel material. This is a level of steerability that's incredibly difficult, if not impossible, with flow-based models because their transformations are global and tightly coupled. Changing one part affects everything. With ARBG, you can effectively intervene at any step in the sequence, influencing only the subsequent parts of the molecule being generated. This capability is highly reminiscent of how you can control the output of an LLM by providing specific prompts or conditions, but applied to the structural generation of molecules. It directly leverages the robustness of autoregressive models to capture that rugged energy landscape, allowing it to generate the complex, sparse configurations needed without getting caught in the topological traps of NFs. This is a crucial enabler for guided molecular design and exploration, moving beyond passive sampling to active steering.
This intervention capability sounds like a game-changer for active exploration and design, moving beyond just passive sampling. Now, let's talk about empirical validation. You mentioned ARBG benefits from LLM scaling properties. Does this translate into actual, measurable performance gains over previous state-of-the-art models? Specifically, what are the key results demonstrating ARBG's superior performance, especially for larger molecular systems, and how does it stack up against previous approaches like PROS or even traditional MD?
The empirical results are indeed striking and conclusive. ARBG consistently outperforms all baseline flow-based methods across every single peptide benchmark they tested. The performance gains are particularly significant in larger peptide systems, such as the 10-residue chignolin, a common benchmark for protein folding studies. To put a specific number to it, the researchers introduced Robin, a massive 132 million parameter transferable model trained entirely within the ARBG framework. Robin significantly improves upon the previous state-of-the-art, which was a discrete time normalizing flow called PROS. On 8 residue peptide systems, Robin reduced the zero-shot energy error, specifically the EW2 metric, by over 60%. This isn't a small incremental improvement. It's a profound leap in sampling accuracy and efficiency. For context, Figure 1 in the paper visually demonstrates this. The right panel shows global and local performance metrics for Robin, PROS, and a short molecular dynamics chain. As you increase the number of energy evaluations, which is a direct and fair measure of computational effort, Robin consistently achieves a much lower EW2 and TICA W2 error, indicating superior sampling efficiency and accuracy than both PROS and MD. The left panel, meanwhile, shows the training loss curves for ARBG models of varying scales, from 8 million to 126 million parameters, on chignolin, illustrating its predictable scaling with increasing computational operations, much like LLMs.
Reducing the zero-shot EW2 error by over 60% on 8 residue systems is an impressive feat. Let's unpack that. First, zero-shot implies generalization to unseen peptides without specific retraining. How crucial is this generalization capability for the utility of such a model in real-world scenarios, where we're constantly encountering novel molecular structures? Second, what exactly does EW2, the energy Wasserstein-2 distance, represent, and why is it such a critical metric for evaluating the quality of equilibrium sampling? Also, you mentioned Tika W2. What does that add to the assessment of performance?
Zero-shot generalization is absolutely paramount for practical utility and scalability. In fields like drug discovery or materials design, you're constantly exploring novel molecular entities or combinations. If your model requires extensive retraining or fine-tuning for every new system, its applicability is severely limited, becoming a bottleneck itself. A transferable model like Robin, capable of generalizing to unseen peptides without specific additional training, dramatically accelerates the discovery process by providing immediate insights into new molecular landscapes. As for the metrics, W2, the energy Wasserstein-2 distance, is a robust and widely accepted global measure of how well the generated distribution of molecular conformations matches the true target energy distribution. A lower W2 means the model is generating samples that are energetically more consistent with the equilibrium state across the entire landscape, not just locally. It effectively penalizes discrepancies across the entire energy spectrum. Tika W2, on the other hand, provides a crucial measure of local performance, specifically focusing on the model's ability to capture collective variables that describe slow conformational changes and transitions between metastable states. So, a low Tika W2 indicates that the model is accurately reproducing the dynamics and transitions between these critical functional states, which is vital for understanding processes like protein folding pathways. Together, W2 and Tika W2 give a comprehensive picture of both global energy fidelity and local conformational sampling accuracy, and Robin's superior performance across both underscores its effectiveness.
So, Robin offers both broad generalization to new systems and highly accurate sampling, effectively capturing both the overall energy landscape and the fine-grained transitions between states. This represents a significant step forward in our ability to simulate and understand complex molecular systems. What are the broader implications of ARBG, and the Robin model specifically, for fields like drug discovery, materials science, or even fundamental biological research? Does this technology fundamentally change the types of questions we can ask or the speed at which we can get answers?
The implications are indeed profound, marking a potential paradigm shift in computational molecular science. By providing a scalable, efficient, and highly accurate method for sampling molecular systems at thermodynamic equilibrium, ARBG and models like Robin directly address a bottleneck that has plagued computational chemistry, biology, and physics for decades. For drug discovery, this means accelerating lead identification and optimization by more rapidly and accurately exploring potential binding conformations and protein-ligand interactions. In materials science, it could enable faster discovery of novel materials with desired properties by simulating their atomic configurations and phase transitions more effectively. And in fundamental biology, it offers a powerful new tool for unraveling the intricate mechanisms of protein folding, enzyme catalysis, and molecular recognition, helping us understand these complex processes with unprecedented detail and speed. The ability to model these complex, high-dimensional spaces with such fidelity and efficiency means we can tackle larger, more intricate systems that were previously computationally intractable, fundamentally changing the scope of inquiry and pushing the boundaries of what's computationally possible in these critical fields.
It sounds like we're moving closer to a future where computational modeling can more reliably predict and understand molecular behavior, truly accelerating scientific discovery across multiple disciplines. This is truly fascinating work and a testament to cross-domain innovation.
Absolutely. The development of autoregressive Boltzmann generators represents a significant advancement, leveraging principles and architectural insights from large language models to unlock new capabilities in molecular simulation. It promises to transform how we approach complex problems in chemistry, biology, and materials science, pushing the boundaries of what's computationally possible and bringing us closer to understanding the fundamental nature of molecular systems.
Thanks for listening to this episode. We hope you gained a deeper understanding of the challenges and groundbreaking solutions in molecular equilibrium sampling. Join us next time for more insights into the cutting edge of science and technology.